Hello, welcome to the video lecture series on digital image processing. So, let us see what is this chromaticity diagram. So, here we have shown this chromaticity diagram and you find that it is a color diagram in a two dimensional space. We have the horizontal axis which is the lowercase which is the axis representing the lowercase x, and we have the vertical axis which is the axis representing lowercase y. That means, the chromatic coefficient for red is along the horizontal axis and the chromatic coefficient for green is along the vertical axis. And if we want to specify any particular color, say for example, I take this particular point and I want to find out that how this particular color can be, say here, how this particular color can be specified. So, as we have said that we can specify it by its chromatic coefficients. Now, two of the components of the chromatic coefficients, that is x and y, that is red component and green component, we can get from the horizontal axis and the vertical axis, and the third component, that is z, obviously in this case will be given by z is equal to 1 minus x plus y. So, x and y I obtain from this chromaticity diagram, and I can get the chromatic coefficient component z simply by using the relation that x plus y plus z is equal to 1. And if you study this chromaticity diagram, you find that all the spectral colors, they are represented along the boundary of this chromaticity diagram. Okay. So, along the boundary we have all the spectral colors. In this chromaticity diagram, there is a point which is marked as say this point, which is marked as point of equal energy. That means, all the red, green and blue components, they are mixed in equal proportion, and this is the one which is the CIE standard of white. Okay. And as we said, the notion of saturation, you find that all the points on the boundary, because they are the spectrum colors, so all the colors along the boundary, they are fully saturated. And as we move inside the chromaticity diagram away from the boundary, as we move away from the boundary, the color becomes less and less saturated. So, one use of this chromaticity diagram is that we can specify a color using this chromaticity diagram. We can find out what are the chromatic coefficients x, y and z by using this chromaticity diagram. And not only that, this chromaticity diagram is also useful for color mixing. Let us see how. Say for example, within this I take two color points. Say I take one color point somewhere here and I take one point somewhere here and I consider another point somewhere here. And if I join these 2 points by a straight line, say like this, in that case this straight line indicates that what are the different colors that I can generate by mixing the color present at this location and the color present at this location. So, all possible mixture of these two colors can create all the colors which are lying on this straight line segment connecting these two color points. And same is true for 3 points. So, instead of just taking these two points, if I take a third point somewhere here, then you form a triangle connecting these 3 color points. Then if I take the color present at this location, the color present at this location and the color which is specified at this location, and by mixing all these 3 colors in different proportions, I can generate all the colors lying within this rectangular region. So, this chromaticity diagram is also very helpful for color mixing operation. For example, we can get some other information from this chromaticity diagram like this. So, as we have said that we have this point of equal energy, which is the CIE standard of white. Now, if I take any color point on the boundary of this chromaticity diagram, which we said that this is nothing but a color which is fully saturated, and we mentioned that is as we move away from this boundary, the colors that we get, they are getting less and less saturated, and saturation at the point of equal energy, which is the CIE standard of white, just we have said, here the saturation is 0, the point is not saturated at all. Now, if I draw a straight line from any of these boundaries joining this point of equal energy like this. Okay. So, this indicates that what are the different shades of color of this particular saturated color that we can obtain by mixing white light to this saturated color. So, as we have said that as we mix white light, the saturation goes on decreasing, that is we can generate different shades of any particular color. So, this particular straight line which connects the point of equal energy, which is nothing but the CIE standard of white, and a color on the boundary which is a fully saturated color, then what I can get is all the shades of this particular color is actually lying on this particular straight line, which joins the boundary point to the point of equal energy. So, you find that using this chromaticity diagram, we can generate different colors. We can find out that in what proportion the red, green and blue, they must be mixed, so that we can generate any particular color. And this we can do for 2 colors, mixing of 2 colors, we can use it for mixing of 3 colors and so on. Now, just to mention that as we have said that we have taken red, green and blue as primary colors, you find that in this chromaticity diagram, your green is, if I take green to be somewhere here, so if I consider this point to be the green point, so this point is the red point and the blue is somewhere here, and if I join these 3 points by straight lines, what I get is a rectangle. So, by using this red, green and blue, I can generate, as we have just discussed, all the colors which are present within this triangular region. So, as this triangular region does not encompass the entire part of this chromaticity diagram, because this chromaticity diagram is not really a triangular diagram. So, just we have said that using 3 fixed wavelengths as red, green and blue, we cannot generate all the colors in the visible region, and that is also quite obvious from this chromaticity diagram, because if we consider only 3 fixed wavelengths to represent red, green and blue points, using those 3 wavelengths we can just form a triangular region, and none of the triangular regions, single triangular region can fully encompass the chromaticity diagram. So, as a result of that, by using fixed wavelengths for red, green and blue as primary colors, cannot generate all the colors as given in this chromaticity diagram. But still, using the chromaticity diagram, we can have many informations, many useful informations. As we have said that we can go for color mixing, we can find out different shades of color, we can specify a color and so on. Now, coming to this next topic, that is color model. Now, we need a color model to specify a particular color. a color model helps us to specify a particular color in a standard way. Now, what is a color model? Color model is actually a space, or we can represent it as a coordinate system within which any specified color will be represented by a single point. Now, as we have said that we have two ways of describing a color. One is by using the RGB model, by using the red, green and blue components, or cyan, yellow and magenta component, which are from the hardware point of view, and similarly from the perception point of view, we have to consider the hue, saturation and brightness. So, considering these two aspects, we can generate two different color models, two types of color models. One color model is oriented towards hardware, that is the color display device or color scanner device or color printer, and the other color model is to cater for to take care of the human perception aspect, and we will see that this will not only take care of the human perception aspect, it is also useful for application purpose. So, accordingly, we can have a number of different color models. One of the color model we will call as RGB model or red, green, blue model, and the other color model is cyan, magenta and yellow, and there is an extension of this, that is CMYK, that is cyan, magenta, yellow and black. This RGB color model, this is useful for image displays like monitor. CMY or CMYK color model, these are useful for image printers, and you find that both these color models are hardware oriented. Because both of them try to specify a color using the components as primary color components, either red, green and blue or cyan, magenta and yellow. And as we have said that red, green and blue, they are the primary colors of light, whereas cyan, magenta and yellow, they are the primary colors of pigments. And the other color model that we will also consider is HSI color model, that is hue, saturation and intensity or brightness, and this HSI color model, it is application oriented or also it is perception oriented, that is how we perceive a particular color. And we have also discussed that this HSI color model, this actually decouples the color from the grayscale information. So, we have said that this I part, this actually gives you the grayscale information, whereas hue and saturation taken together gives you the chromatic information. So, because of this, as in HSI model, we are decoupling the intensity information from the chromatic information. So, the advantage that we get is many of the applications or the algorithms which are actually developed for grayscale images, they can also be applied in case of color images, because here we are decoupling the color from the intensity. So, all the intensity oriented all the algorithms which are actually developed for grayscale images can also be applied on the intensity component or I component of this color image. Now, first let us discuss about the RGB model. So, we will talk about RGB color model first. As we have said that in case of RGB, a color image is represented by three primary components, and the primary components are red, green and blue. So, these are the three components, three color components which when mixed in proper form in appropriate proportion, this generates all possible colors. So, our RGB color model is based on Cartesian coordinate system, and we will see in this diagram that this shows diagrammatically an RGB color model that we normally use. So, you find that this RGB color model is based on the Cartesian coordinate system, where the red, green and blue R, G and B, these components are placed along the coordinate axis, and the red component is placed at location 1, 0, 0 as shown in this diagram. So, this is the location which contains the red, this is the location 0, 1, 0 which is the green point, and 0, 0, 1 this is the blue point. So, we have this red point, green point and blue point, they are along three corners of a cube in this RGB in this Cartesian coordinate system. Similarly, cyan, magenta and yellow, they are at other three corners in this cube. Now, here let me mention that this model which is represented, it is in the normalized form, that is all the three color components, that is red, green and blue, they are varying within the range 0 to 1. So, all these color components are represented in a normalized form. Similarly, the cyan, magenta and yellow, they are also represented in normalized form. Now, the origin of this color model, that is at location 0, 0, 0, this represents black, and the furthest vertex, that is 1, 1, 1, that represents white. And you find that if I join a straight line connecting the origin to this white point, so this straight line actually represents a grayscale, and we also call it an intensity axis. So, as you move from the origin which is black to the furthest vertex in this cube which is white, what we will generate is different intensity values. Okay. So, as a result of this, we also call it the intensity axis or grayscale axis. So, we stop our discussions today. We have just introduced the RGB color model, and we will continue with our discussion in our next class. Thank you.